We're starting with Fajan's rules. Uh, if we take up, Fajan's rules are basically meant for finding out the covalent character of ionic solids. You know that none of the solids can be completely ionic or completely covalent. All ionic solids have some covalent character in them, just as all covalent solids can have ionic character in them. Now, how do we get covalent character in ionic solids? It is very simple. That generally in any ionic solids you have the positive cations and you have the negative anions. Generally, the anions are bigger in size and they have a cloud of electrons around them. Now, when a small cation comes very close to this negatively charged anion, we find that there is some distortion in the electron cloud, and the electron density starts getting close to the cation, and this is called polarization. And this polarization can induce covalent character in molecules. Now, it was Fajan who for the first time studied the covalency of all ionic solids, and he suggested a set of rules by which one can very easily know which of the ionic solids may have more covalency in it and which of the ionic solid may have a little lower covalency. So let us understand these rules one by one. The first rule says that smaller cations have higher charge density, and these smaller cations are able to cause more polarization of larger anions, and therefore smaller a cation, more is the polarization of anion, and thus more is the covalency, and therefore we say smaller cations cause more polarization and hence induce higher covalency. Example, you can take example of a smaller cation Li. LiCl is more covalent than NaCl, where Na is a little larger than Li. The second rule says that just as cations have to be as small as possible for higher polarization, we can say that larger anions undergo more polarization. You know that larger anions, they have a huge electron cloud, and therefore they undergo higher polarization, and because of which there would be more covalency induced in a molecule. The best example is NaCl, which is less covalent than NaI. Why? Because iodine here is larger than Cl. So this is more covalent. NaI is more covalent than NaCl. Right? So that's the second point. The third point now is about we have the charge. Cations having higher charges, right, can induce more polarization. That's but obvious. If you have two cations like Na plus and Al plus 3. On one side, Al plus 3 would be smaller, and on the other side, because of a plus 3 charge, it would have a much higher charge density than Na, and therefore Al plus 3 would be able to cause more polarization of anion than Na plus, and therefore we say NaCl, right, is less covalent than MgCl2, which is less covalent than AlCl3. Why? Because Al here is having a plus 3 charge, Mg has a plus 2, and Na has a plus 1 charge. So AlCl3 here is the most covalent molecule. Just as you have, charge for cations, in the same way, we also have, the same applies for anions also. Any anion with a higher negative charge would always undergo more polarization, and therefore, if you talk about, any anion with a higher negative charge, right, it would always form a more covalent molecule. This can be, very easily explained on the basis of, you can take AgCl and you can take Ag2O, right? Oxygen has a -2 charge, so talking about the covalency, Ag2O would be more covalent and AgCl would be less covalent. Thus, this is because oxygen here has a -2 charge and chlorine here has a -1 charge. So, anions with higher or more negative charges would undergo more polarization. That's one more rule. At times you come across cations which have the same charge and more or less similar size. They may not vary much in size. Now in that case, how do you decide which of them would form a more covalent molecule? Now in such cases you will have to find out the configuration and the number of electrons that the particular cation would have in its valence shell. The cation with 18 electrons in the valence shell, right, would always form a more covalent molecule than a cation with 8 electrons in its valence shell. For example, you talk about NaCl, right? Sodium chloride has Na in +1 state. Na in +1 will have 8 electrons in its valence shell. However, you talk about you compare this with CuCl, right? Copper, right, will have a copper has 18 electrons in its valence shell, because of which we say NaCl would be more ionic and CuCl would be more covalent. Thus, checking the covalency, NaCl is less covalent, CuCl is more covalent. The only difference here is copper in its valence shell would have 18 electrons, Na in its valence shell would have 8 electrons. Both are in +1 state, right? So these are the Fajan's rules, and these rules can help you decide the covalency of different ionic solids.